broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Welcome to another edition of our AMS Webinar series. Today, we're going to be talking about machining molds and castings. My name is Joe Anand. I'm the product manager here at MecSoft, and I'll be joined today by Don LaCourse, a senior application engineer, who's going to be actually doing the majority of the show and tell here.
Hello, everyone.
Don, if you want to switch to the next slide, please. Okay, so before we get started, we want to keep this webinar as interactive as possible. So you can use your chat window for questions. As the webinar is going, as Don's showing things on the screen, you can actually input your questions in the chat window. I'll be in the background listening for these questions, and I can answer them if I can. Or if you need something that Don needs to slow down or show something in more detail, we can also do that. Typically, we also reserve the last 10 minutes for questions and answers, depending on how we're doing as far as the time frame is concerned. But we would really like to keep it as interactive as possible. So go ahead and use the chat window whenever possible or whenever you have a question. And as usual, the recordings of this webinar will be made available after the webinar. Give us a day or so to clean it up, and we will send out an email with the YouTube link for the webinar recording for all those who have registered. As far as the agenda today, we're going to be starting initially with the overview of common mold types, the different types of molds that people use in the industry, and the different types of molds that we can machine in our product, as well as the mold type that our customers are generally machining. We're going to be talking about general CAM strategies for creating these mold cores and cavities using the 2- and the 3-axis toolpath methods in our system. And also, we'll talk a little bit about choosing the right toolpath methods to achieve the best results that you're looking for. And then also some power techniques in terms of tips and techniques for parting line machining, which is very important for mold makers, especially for plastic injection molding. And then also, we're going to be talking about some of the advanced machining methods we have in our system to allow you to get these types of molds machined in the best possible manner. Before we get started, I also want to tell you that the best product for you if you're a mold maker would be the combination of Rhino and Rhino CAM, and also the configuration that we would recommend for mold makers would be the Rhino CAM Pro configuration. So keep that in mind as Don is going through the demonstration. All right, Don, take it away.
Hello, everyone. Thanks for being here with us today for our mold machining webinar. We're going to talk a little bit about the different types of castings and molds that typically our product is used to machine. And I've lined these up from left to right in order of accuracy required. So on the left, we've got thermoform examples. And if you notice, take a look at that graphic on the left. Thermoforming, it just drapes a heated sheet of plastic over a core model. So all your machining in our product is the actual core. And so you don't have to machine any cavities or anything. And typically the tolerances are relatively loose. The only thing you need to make sure is that you have the right amount of draft, because that plastic has to slip off of that core very easily. So in the middle, we move from thermoforming to casting. Now casting, in casting, you need to machine both a blank in order to create the cavities. It's kind of a different way of doing it than injection molding, where you're just shooting in plastic, in a core and cavity. In casting, you are actually molding the cavities from a blank. So you got to create that blank, machine that blank ahead of time, and then you use that to mold or to form each half of the mold. And the material is like a green sand that's sticks together, and it creates a cavity from that blank. And on the right, obviously, and we're going to be spending most of our time on plastic injection molding. And just as an overview, plastic injection molding, you're using cores and cavities and injecting various plastics, ABS, polypropylene, many different types of plastics under very high pressure into these cavities. So this, we're going to be talking about the core. If you look at this graphic, you see the cavity there in yellow. So we're going to be talking about primarily in machining the cavity half of this mold. So these are inserts that you insert into the mold in order to create the cavity in order to, obviously, to injection mold it. Let's go to the next slide. Now, first, we're going to talk about the thermoforming. As I mentioned, in thermoforming, you're just machining a core blank. And in thermoforming, there's a picture of it right here, a couple examples. On the left, we have an example from the Warren Group, which makes thermoform packaging, display packaging, and also product packaging, where they're draping clear plastic over a core mold in order to create the end product. And then on the right, we have an example from South Dakota State University of a student project where the core components are machined out of stock material, and then they're set on the thermoform machine, and then the plastic is formed over it. So thermoforming, like I mentioned, is the least amount of accuracy that you need to worry about, primarily draft. So you want to make sure you have enough draft to get that plastic up off of that core. Now, next up is cast mold examples. I mentioned previously that you need to have a blank in order to create a cavity, in order to create a casted part. And the final casted part is obviously the part you're going to machine, which is your production component. But uniquely, you also have to create the blank. So you have to machine that as well. And then you use that. If you look at the section view on the left, it shows the two halves of the casting mold in orange. And then the casted material is poured into the gray areas, so to form the actual product. If you move over there to the far right, this is the end result of the casted product. So you're going to be machining the blank, and you got to be machining the final product. Just one second. Okay, here's another example of a cast molded part where, again, you have to have a blank. So we have the casted blank over here on the left side near the bottom, and that needs to be modeled and created. Now, you can actually, in order to create this blank, you can also create a prototype mold with a cavity and core in order to mold the blank. The blank doesn't have to be obviously as accurate. It's, as your finished product, because you're going to be machining this blank in areas that are functional for this part. So in the top and right areas, we show both sides of this blank after they're machined. So you got machining on one side, and then you flip it over, and we have fixture plates to illustrate that process. Again, if anybody's got any questions, put them in the chat window, and we'll get to them. Okay, so that's another casted mold example. Now, the big guy on the block, insert injection molding. So there's a lot of things on this screen, so I'm going to go a little bit in detail and start from the right top area. So we have our end result product, which is a pair of sunglasses. You don't see through them. They're all plastic. They're probably molded in black plastic. So below that, you see one half of the cavity insert, okay? And then below that, you see the same insert with a protection surface draped over it. And we're going to talk in detail about these protection surfaces and how they're used to machine the inserts, but primarily what they're used to protect the parting line. And if you move over from there in the middle, you see two examples of injection molding defects. On the right, you see flash, which can occur if your parting line has been sufficiently degraded. So you need to take care of that parting line, and we're going to show you how to do that. And then on the left shows a mismatch in the parting line. Now the mismatch can occur if your tolerances aren't tight enough, if your setup is not correct, things of that nature. So on the right, we got the flash, which is caused by degrading of the parting line. And then on the left, we have mismatch, which can be caused by incorrect setup or incorrect tolerances. So let's move directly above that. Now, a subset of cavity and core inserts in a mold. Obviously, you think of a mold, you think, okay, we're just going to blow some plastic in it, and then we're going to have a part, and then everyone's hunky-dory. But that's not the case. You will have a prototype mold, which will create some prototype parts. Your engineering customer will review those molds. They'll make changes. They'll take the parts. They'll mark them up. They'll actually take a marker and write it, write on the part. Say I want more material here. I want less material there. We need to make revisions. So the mold maker will make sets of inserts. So he's probably going to machine at least 2 sets and possibly even more, just for that purpose, for revisions and whatnot. And if those revisions get to such an extent that the mold cannot be revised anymore, either by adding material into the mold, and this is done regularly, they'll actually, in a typically welding process, where they'll add material into the cavity so that they can remove it, with revisions in it, or more precisely, they can cut holes in that insert using a wire EDM machine to get a precise insert measurement, where you can redesign an insert to go in the insert, which contains the revision. So this is, primarily the reason why precision is the utmost concern in plastic injection molds. Now on the far left.
Just a note here, I just wanted to let you know, Don in his previous life was a mold maker, and so just wanted to let you know he knows what he's talking about. So just to give him a little bit of encouragement here.
Well, just a note here, I could only hack mold making for 2 years. It was very, very demanding. And you guys know, if you're making molds, especially if you're in the automotive industry or aeronautics industry, it's a very demanding profession to be in. So hats off to you guys for being able to stick it out longer than I was able to. Okay, so on the far left, if you've created cavities, then you know about EDM machining, electronic discharge machining, where you're taking a core and a cavity, and one half of the cavity is typically it's made out of graphite, and it is used to actually burn a cavity into your insert. Both the cavity and the graphite are submerged in a dielectric solution, and the precision that these two components are getting closer and closer to each other, about 4 thousandths apart, the electricity starts arcing from from your insert to your graphite, and both parts are actually vaporized in the process. but what you're left with is a perfectly formed cavity that you don't need any finishing, you don't need to do anything else. So this is a very, as long as your graphite core is machined properly, that's exactly what you're going to see in the cavity. Okay, so if anybody has any questions on mold inserts, please put them in the chat window. So when we get to the demo area, we're going to be spending a lot of time on this particular part, and I'm going to show you the best way to machine those parting lines. Okay, here we have, I wanted to use just a basic insert example to illustrate the techniques I'm going to show you. What we have is a very basic insert. We have a cavity, we have a parting surface around the cavity, and then between the two, we have the parting line. And we're going to show you the best way to machine the cavity as well as the parting surface and how to protect that parting line. If you don't protect that parting line, mold makers, you understand, if you don't protect that parting line, you're not going to be machining molds for very long. So your customer will just give it back to you and say redo it. So you don't want to do that. Now, we're also going to talk about some tips. Joe mentioned some tips and techniques for machining. These apply to plastic injection mold. So from here out, as far as the demo portion, we're primarily going to be talking about plastic injection molding, but we're going to just show you some parts as well for the other two. So if we start up on the left, we have, it's called dial in your accuracy. Now, obviously, for injection molding inserts, the accuracy is very great. You'll be dialing in this accuracy. The precision is very high on these inserts, especially in the parting line area near your cavity and your parting plane and your parting surface. And we're going to show you how to dial in that accuracy. From there, we'll go down to the cutting tools. We're going to talk a little bit about as a generic rule, which types of tools are better to use than others. And then over here on the bottom right, we see what we call them protection surfaces. So we're going to show you how to add protection surfaces to your inserts in order to protect them while you're machining them. And then up on the top right, we're going to show you what I'm calling the first contact rule. And I'll get into that in more detail. But basically from the illustration, you get the gist of the rule. And we'll go into that in more detail in just a moment. Oh, let me go back one. Okay. Dialing in your accuracy. We have 6 areas in RhinoCAM that you want to check and adjust depending on the accuracy requirements of your customer. And typically you will start in the arc fitting tolerance. Obviously, if you're fitting arcs on your cavity, you want that to be your final highest resolution accuracy. And from there, we'll back off and do the CAM operational global tolerance, and I'm going to go through these and show you in the part. But typically, you want to do your arc fitting tolerance. In our example, we're starting with 1,000th, and then the CAM global tolerance is half of the arc fitting tolerance, so that would be 0.5 And then we're going to look at setting the CAD geometry tolerance. So we're adding 2 more decimal places to that, just for rounding. And then we're going to look at how to adjust the CAM part sampling resolution. This is a setting in the CAM preferences which affects your accuracy of your machining. Also, we're just going to touch base on the tool just to make sure that you have all of the decimal places filled out on your tool. If you need a 3/8 tool, don't enter 3.37, okay? You want to use all the decimal places you need to fully define that tool diameter. And then lastly, but not leastly, before you post, you want to go into your post processor and make sure that you have the correct number of decimal places being posted. If you do all of them, 1, 2, 3, 4, and 5, but you don't adjust the output in your post, it's all for naught, because you won't see it in the output coordinates. Again, any questions? Everyone holler, okay? Okay, the next tip or technique is for the cutting tool. Basically, what we're trying to get across here is that you want the stoutest cutting tool that you can use, the largest diameter, the largest shaft diameter, which will, and the shortest length of the tool, which will create a very strong tool. It'll eliminate any deflection in the tool, and that's what you want. And then, and on this tool, we show a taper. Obviously, if you have a part that needs draft and your part doesn't have the draft, then obviously you're going to want to use a taper tool in order to machine that draft automatically. So on the right, we see a no-no. We see a long, narrow tool, small diameter, a lot of deflection going on in that tool, especially if you're machining hard materials. Sometimes you'll have to come back and do revisions after that. Those inserts have already been heat treated. So very strong steel that you're going to have to cut. So you want to stay away from very long tools, which can affect your resolution and tolerance. Now, the third technique we're going to show you is the protection surfaces. And by protection surfaces, in our example insert, you see that we have added extensions to the cavity surfaces, and we have added extensions to the parting surface of the mold. So here on the parting surface, you see that it extends out past the mold on each side. And these are really, they're not complex to create, and I'm going to show you how to create them in Rhino. And Rhino is the best product to use for, in my opinion, to use for injection molding, especially for the surface modeling that you're going to need. So on the right, we see the cavity extensions and how they're extending up past the parting line. And as the description testifies, these surfaces are playing interference with your parting line. It's protecting it from the tool. So we don't want the tool to beat up on the parting line. You don't want it to run over the parting line. You don't want it to roll over the parting line. And you don't want it to roll along the parting line. You want a nice clean cut across that parting line. And we're going to show you how to achieve that. Now, in our example part, we did do, ahead of time, I did the roughing and re-roughing of this part. And just as a note, in the re-roughing, that is a Pro configuration toolpath. In the Pro and Advanced 3-axis, you get a whole range of toolpath methods that can use exclusively for mold making. And we're going to go over those a little bit later. So the final technique I guess we're going to get across is what I'm calling the first contact rule for machining parting lines, cavities, and parting surfaces. If you consider yourself the tool and you're running along this parting surface and you hit that parting line, the first contact rule states that you will not touch that same point on that parting line again in the same operation. So that tool will just say, howdy parting line, I'm going on my way. It's touched it and it's continuing to cut in other areas. It doesn't stop on the parting line. Like I mentioned, it doesn't roll over the parting line, and it doesn't roll along the parting line. And that's what these protection surfaces are used for. So they're going to show you, basically I'm telling you how to do it, but we're going to show you the end result of using this technique and not using this technique. And it's very stark comparison. Now, we see here, after using the first contact rule and not using the first contact rule. So on the left, we have the cavity machined out, and we have the parting surface machined out. On the right top, you will see the cavity, cut material simulation of the cavity, the entire insert with the first contact rule implemented. So you see a nice, clear parting line, very distinct. There's no colors bleeding from one side to another. And if you go in the middle image, you'll see that. You'll see areas where the cavity is bleeding over into the parting surface and vice versa. This area, you're allowing the tool to literally beat up on the parting line, and that's going to cause flash. Not so much mismatch because of your accuracy, but you're going to get flash, and you're going to see this in your prototypes when they come out of your insert. Out of your cavity inserts, and you're just going to be throwing this cavity in the trash bin because it's not any good. And here's just a close-up of the one contact rule on the right, nice and clean, very precise, no bleeding from one side to another, versus on the left. And this is literally how your insert's going to come out. I mean, you're going to be machining up on your parting surface when you're supposed to be machining your cavity, and vice versa. And there's nothing you can do about this if you don't use these protection surfaces. And I'll show you that as well. Joe, is there any questions? If you have any questions.
No, you're doing fine, Don.
Okay.
There's some comments, but
okay.
There's a lot of experts seem like to be watching today, so they know what they're doing. So
okay,
continue,
great.
please.
Okay, so there's our first contact rule up close. Now, we have published some documents and articles relating to mold insert machining, parting line machining. I'm going to put, when we send you to the webinar replay, I'm going to put links in there that where you can get to these articles and read them for reference. And then finally, depending on how much time we have left over, we're going to show you some of the advanced professional configuration techniques and how they are used on a particular cavity and core molds. Okay, let's get into the demo. First thing I'm going to do is I'm going to go over the thermoforming and then the casted parts. We have some already programmed up, and I'm going to show you those. So first up is the component from the Warren Group. They make thermoformed packaging and display packaging. And again, as I mentioned, you're generally machining a core side of the mold, and the thermoform plastic is going to be draped over that. So everything of concern here primarily is just the amount of draft you have on the cores to make sure that they come slipping out of that thermoform plastic, and you can see the draft here. And then on the right, typically, these are typical operations that you would use basically for any component. Just roughing, finishing, basic profiling, engraving, and then 3-axis parallel finishing on the top, at different offsets. So let's go over to the casted examples. I have 2 casting examples I want to show you. In this example, and I want to mention here that in order to create your stock, which is going to be the stock is going to represent your blank. Okay, so this is the part that's going to come out of the casting, and this is the part you're going to machine. So there's 2 different ways you can create that stock. You can actually model your blank, and I'll show you here. Turn that on, turn that off. So this is the blank, and you can use that to create your stock. just by using the stock from selection. So that'll end up being your stock. So with the stock on, let's show it. And let's turn the part off. So here you can see the stock in transparency. I have some of the masking surfaces on, so let's go turn them off. So basically, you machine, in this particular example, you machine the bottom and then the top, both sides, and you use protection surfaces in various, depending on what you're machining, in order to protect different areas of the component. So let's go over and look at the top again. So on the top side, again, you'll see in the machining job tree, you'll see it says spiral finish with mask number 3. So we got to turn on mask number 3. So this is turned on when you generate the tool path. So it keeps the tool from plunging down in these cavities and protects various areas. So that's another method of using the protection surfaces, not only for parting lines, but also just to guide your tool to where you want it to go, or more specifically, where you don't want it to go. And again, we got other, operations to fill out the entire component. Okay, got one more casted part I want to show you before we get into the injection molding. So here is a cast. What you're seeing here is the stock. And that stock model was created from a casted blank. So we turn our stock off. Here's our casted blank that was modeled from the actual component. So you can
that casted blank is actually modeled in Rhino, correct?
Right. Yes, it is. And again, there's two different methods. In order to, if you don't have time to create your casted blank, model it. If you don't have time to model it, or if you don't have the enough information to model it, you can take your actual part and you can use it to create your casted blank just by offsetting the surfaces. If it's a solid, you can do a general offset, or you can use the stock part offset, part box stock, which allows you to add material on all sides of your part, and you can use that in order to create your stock. Okay, so any questions about either one of those casting examples, just put them in the questions bar. I'm going to hop over to injection molding real quick. We're going to be taking a look at some recommended techniques for programming injection molding cavity inserts and core inserts. In this video, we're going to introduce the use of what we're calling protection surfaces. These are added surfaces in your model that help protect the parting line during machine toolpath generation. Okay, so I've got a simple insert on the screen. We have one cavity, we have a parting surface, and it is exploded to be a poly surface. It's not a solid. In order to edit the surfaces, you need to explode your solid. So what we're going to do first is we're going to program this without the use of protection surfaces so you can see the cut material simulation at the parting line. So we're going to go ahead. We have the roughing and the re-roughing already completed. So we're going to go ahead and create a 3-axis parallel finishing operation. And we're going to go to the Part Surfaces tab of the Control Geometry tab, and we're going to select the surfaces, and we're going to pick our 4 cavity surfaces, and then right-click. For the surfaces extent condition, you can set it to on, to, or past. On means that the center tip of the tool will go to the parting line and line up with the surface edges, which in this case is the parting line. The 2 option means that the diameter of the tool will stop when it lines up with the boundaries of the surface, which means that your cutting point, the tip, will not go all the way to the end of the surface, so we're not going to use that. The past option is where the diameter of the tool goes past the surface boundary and stops when it touches the other side of the tool diameter. Also, we don't want to use that because we want to keep the tool off of these parting surfaces. So we're going to use the on condition. And for the tool, we're going to use a 3/8 inch ball mill. For the cut parameters, we're going to set the intolerance to 0.0005 and out tolerance 0.5. And this is 1/2 of a thousandth. And the reason is that we're going to set our advanced cut parameters to 1,000. So we're starting with the advanced cut parameters and we're setting it to 1,000, and then in the cut parameters we're setting it to 1/2 of that. That's what we recommend. So also for the cut parameters, we're going to have a mixed cut direction, start at the bottom. We're going to have an angle of cuts of 0, which means the cuts will traverse back and forth in the x-axis. And for the step over, we're going to make it 5 thousandths. Typically, you may make it tighter in production environments, but we're setting it to 5 thousandths just for show. So we're not going to change the Z containment. The entry and exit tabs, we'll leave all those the same. And for the advanced cut parameters, as I mentioned, we set the before mark fitting to 1,000ths, and let's generate that. Okay, so let's look at the toolpath. We see that we have cuts running along the x-axis. The dark blue are arc motions, and the light cyan are linear motions. And we see that the tool goes up and aligns with the parting line. Okay, so let's go ahead and also change the color of this operation for when we simulate it. Okay. So now we got one parallel finishing operation. We're going to clone that, and we're going to use it again, and we're going to change our cut direction to 90 degrees. So it'll be right angles to the first one. And here's our toolpath in the Y direction. Now what we're going to do also is we want to program toolpaths for the parting surface themselves. We'll make a copy or clone a copy of the last parallel finishing operation. We're going to edit it, and we'll go to the part surfaces tab. We'll remove those, and we're going to select the parting surfaces. So we'll select surfaces. We'll pick our parting surfaces, work our way around, and right click. So here's our parting surfaces that we're going to machine. We're going to use the same on condition where the tool will go up to the parting line or the edge of the insert and stop. Everything else is going to be the same. We're going to leave that cut angle we'll set it to 0 like the others, and we'll pick generate. So here's our parting surface parallel finishing. And we're going to change the color of this to a darker blue for contrast. So we've got our first parting surface parallel finishing completed. We're going to clone that, and we're going to edit this one, and the only thing we're going to do here is we're going to change the cut direction to 90 degrees to traverse in the y-axis. So there's our parallel finishing in the y-axis of the surface parting surface machining. Okay, so we got those. Let's go ahead and look at the simulation and see how that looks. So let's go ahead and we'll just simulate them individually. There's our roughing. There's our re-roughing. Here's our first cavity parallel finishing going in the X direction. And then here's our second cavity finishing going in the Y direction. Okay, so there's our cavity finished. And let's go ahead and simulate the parting surface in the X direction and in the Y direction. So the tool is going up to the parting line, and the tip of the tool is stopping when it aligns itself with the parting line. And the same occurred in the cavity. So let's take a look at this. Let's look at the top view. And we see not so good a parting line. We got some overcutting here. This will probably end up with flash in these areas here, as well as right here. And let's go back and look at the isometric view again. So you see how the tool rode up on to the parting line and cut into the parting surface. So if you look, here's the parting line here, and here's the cut. So it went up to it, and when it stopped, it started cutting into the parting surface, which, you know, that would be a flash area and not a very nice parting line. And on the other side, you see that it rode the parting line even further. This is the parting line. So the tip of the tool was here, and it gouged out part of your parting surface. That's not a very good parting line. If you try to mold a part with that, you probably end up throwing the parts away. We don't want to do that. Okay, so there is the typical method of machining a cavity in a parting surface. Now what we're going to do is we're going to show you what happens when you use protection surfaces. Again, a protection surface is just a regular surface, but what it does is it protects the parting line. That's its sole purpose. It keeps the tool from riding on the parting line, rolling over the parting line, or riding along the parting line. So if you refer back to in our slide presentation, the first contact rule states that whenever that tool makes first contact with the parting line, that's it. It doesn't contact that point again. It doesn't roll on it. It doesn't do anything. It just contacts it and just keeps on going. And that's in both for the cavity areas and for the parting surface areas. Okay, so let's go ahead for the protection surfaces. We're going to create a couple of layers. We'll say surf 1-cavity. And we'll create one more, call it surf 2. Okay, for our parting protection surfaces, we're going to go ahead and make a copy of these cavity surfaces. And we're going to copy them to this layer. So what we're going to do now is we're going to activate that layer, turn our other layers off, and you see that we have just the cavity surfaces. What we're going to do, Rhino provides a command that allows you to untrim a surface. So instead of the trim surface, this surface will extend out to its full extent, untrimmed. So we're going to go to the Rhino surface menu, go down to surface edit tools, and we're going to select untrim. And it's asking you to select an edge. So we're going to pick this edge. So you see how the surface extended out. We'll pick this edge, and that edge. So there's our cavity surfaces untrimmed. And let's go ahead and escape out of that, and we'll just change the color of these protection surfaces, just so we have some contrast. Okay, so there's our protection surfaces for the cavity. So now we'll go over to our layers. We will activate Surf 2 and turn off protection surfaces for the cavity, and then also turn on the part itself. So what we're going to do here is we're going to create some parting surfaces from the edge geometry that we have. So the first thing we're going to do is we're going to go to Surface, Extrude Curve, Straight. So what we're going to do is we're going to extrude these edge curves right across the cavity to cover it. So we're going to pick this edge, this edge, this edge, and this edge here. And we're going to right click, and you'll see that it's extruding in the default direction of the parting surface. So what we want to do here is we don't need to know exactly how far it's going to overlap. We just need to make sure that it's at least a half of the tool radius. So we're going to bring it over a little excess. You see that you can see through the surface. That's because it's upside down. So we'll select them and type in flip, and that turns them right side up. And then we're going to select them again, and we're going to drag them across the top of the cavity. So what we have is the cavity completely covered over. That's what we mean by a protection surface. Now also we're going to be machining these edges of the parting surfaces, so we want to extend surfaces out on each side. So we're going to go to Surface, Extrude, Curve, Straight. This time we're going to extrude the edge of the parting surface, protection surface we just created. We'll right click, and you'll see that by default it's going in the vertical direction, but you can change that by selecting the direction option from the command line. And we're going to pick 2 points to determine the direction. And then we're going to slide out the surface in that direction. Again, it's flipped upside down, so let's go ahead and select it. Select flip, and that'll turn it right side up. So we're going to do the same thing, Surface, Extrude, Curve, Straight on the other end. And for the direction, we're going to pick 2 points, and we're going to extend that out there. So here's our parting surface completely covered with a protection surface. So what we're going to do is we're going to go to the top view, and we're just going to select those, and we'll change the color. There. Okay. So now we got our protection surfaces created. There's our cavity protection surfaces, and there's our parting surface protection surfaces. So now what we're going to do is we're going to use the same operations, and we're going to regenerate those with the protection surfaces displayed. So we're going to go ahead and select all 4 of our parallel finishing operations. We're going to copy, and we're going to paste. So these have another copy, and we can go ahead and suppress these so that we don't accidentally use them or edit them in any way. So we're going to go into our first cavity parallel finishing operation, and what we're going to do is we're going to you can either leave the part displayed on or off. In this case, we do, however, have to turn off the parting surface so we can get down to the cavity. So we're going to edit that, and we're going to go to the Part Surfaces tab. We're going to remove all of those, and we're going to select the protection surfaces. There. So in this operation, it's going to go all the way. It's going to ignore the parting line. It's going to go right past it and go right to the edge of our protection surface. Let's go ahead and generate that. So you can see how the toolpath went right past the parting line, right up onto the boundary of the protection surface. So let's do that again for the second cavity operation. Go to the Part Surfaces tab. We'll remove all, and we'll select our untrimmed protection surface. Right click, and then generate. So there is our toolpaths for the cavity using protection surfaces. Now let's go ahead and edit the two for our parting surfaces. So if we're going to turn off our protection surface for the cavity and turn on our protection surface for the parting surface. So we're going to edit the first operation in the parting surfaces. Go to the Part Surfaces tab. In this case, we don't need to change our selection. We're going to leave it the same boundaries as it was before, and it'll just ride over our protection surfaces. So we're going to go ahead and pick Generate, and we're going to go to our second parting surface operation and pick Generate. So there's our parting surfaces. Let's turn off the protection surfaces so you can see how it goes past the parting line. Actually, for this one, we want to go ahead and make an edit here. Let's go back to the Part Surfaces tab, and we're going to use the past condition. Now in this case, because our protection surface is displayed, we can use the past condition because it'll go past the parting line and stay out of the cavity because we have this protection surface displayed. So we're going to generate that, and then we're going to generate this one also and change it to past and generate. Okay, so let's turn off our protection surfaces so you can see how it travels past the parting line onto our protection surface. Okay, we've got all of our operations completed. Let's go ahead and simulate those. We need to regenerate our roughing, and then we will simulate our roughing. Then we'll regenerate our re-roughing, and we'll simulate our re-roughing, and we'll turn the toolpaths off so we get a good look. And now we're going to skip our locked operations, go right down to the parallel finishing operations that we used with our protection surfaces displayed. Now again, the only thing you have to do is make sure your protection surfaces are visible. You don't have to select them in any special way. As long as they're visible on the screen when you generate the operation, they will affect your toolpath. So let's go ahead and simulate our first parallel finishing in the cavity. And we'll simulate our second parallel finishing in the Y direction of the cavity. So now we're going to simulate the parting surface toolpaths. We're going to simulate that in the X direction, and then also in the Y direction. Okay, so let's look at the top view again. So now you see a real clean and crisp parting line. Let's go into the isometric view, and you'll see that there's no over bleeding. The tool is not riding over the parting line. It's not these colors are not bleeding one into the other. This means that the parting protection surfaces did their job and forced that tool to ride directly over the parting line without stopping on it, without rolling over on it, and without rolling along it. So all you want to do is to have that tool touch the parting line and then move on. So we hope this short video helped you to understand some methods that we recommend for machining inserts, injection molded inserts, cavities, and parting surfaces and parting lines. In this section, we're going to be talking about using 3-axis advanced toolpath methods to assist you in machining a cavity/core mold plate. We have a core mold plate just loaded, which contains various poly surfaces that need to be machined. Now we have some machining operations already loaded in this file, so let's just go over them real quickly. We have a roughing operation, and a reroughing operation to clear material away from the core region. And the reroughing is a professional configuration toolpath method. And we have some additional reroughing to get some more material off of the part. And then we have a series of finishing operations. These operations are not required for the professional configuration or advanced 3D machining methods, so we added these to the file beforehand. So we have a horizontal finishing to finish the part from the parting plane up to this height, and then we also have a second horizontal finishing operation to clean up the bottom edges of the core. And then we have a few parallel finishing operations that flow with the geometry, and this is what you want to do as far as your any operation you use on a mold cavity or a mold core. You want the tool to flow with the part geometry, not against it. So we have a parallel finishing operation, and it's going in the X direction, and we are fitting arcs to that tool path. So you see nice blue arc motions all the way down the length of these radial regions. And also we have one in the mid area, parallel finishing with arc fitting. The tool path going in the Y direction. And then we have another tool path going in the Y direction, parallel finishing, as you can see here. And then we added a 2-axis profiling operation just to clean up these flat areas here and here. Okay, but that leaves a lot of areas that still need to be machined, and advanced 3-axis methods or the Pro configuration has the toolpath operations that you need or would want to have to machine this type of mold core. So first off, we're going to machine these surfaces in here, and we're going to use a 3-axis advanced when we're going to use 3D offset pocketing. And 3D offset pocketing, you can consider it like a net that you throw over the part, and the cut offsets are consistently spaced, irregardless of the topology of the part model. So you have a consistent step over in both the X and the Y, and following the contour of your part. So we're going to go ahead and go to the Part Surfaces tab. We're going to use the Select Surfaces button, and we're going to go in and select these surfaces here. Okay, so we got our surfaces selected, and we're going to use the on condition, which means that the tool will go up to the boundary of the curves but not extend past it. So for the tool, we'll use our 1/16 inch ball mill, and clearance plane, feeds and speeds, they're not irrelevant to what we're talking about here. So we'll go straight to the cut parameters tab. We have a tolerance set, and we're going to use a mixed cut direction. We're going to start cutting on the inside, which means it's going to start in the middle of this area and work its way out. And then for a step over, let's go 0.01, say, for practical purposes, and for the entry and exit, we'll leave that as linear entries and a linear exit. So let's generate that. Okay, let's zoom in on that. What you see here is a constant 3D step over that encompasses the surfaces that you selected and follows the contour of the part. Now the reason it didn't drop all the way down to here is because we had the 2 option selected. So if you go to the top view, you'll see that it lines up perfectly with the edges of the geometry that we selected. Okay, so the next area, we have some additional similar areas in this region here. So we're just going to clone this operation. We'll open it up. We'll remove those surfaces, and we'll select these surfaces here. Okay, and we'll generate. Again, we have a consistent 3D step over following the contour shape of these surfaces. And this operation is only available, again, in the Pro or 3-axis Advanced configuration of the product. So we got some additional areas here that we could use this on. So let's go ahead and clone this again. And we'll open it up, and we'll remove our part surfaces and select these surfaces here. And hit enter and generate. So again, you see, if we look at the top view, we have perfect coverage of these surface areas, and the toolpath is a constant 3D step over, and it follows the contour of these surfaces. Okay, so we got some other areas that we need to machine. Back in this area, looks like we could use the 3D offset pocketing here as well. Let's go ahead and clone that. Remove the surfaces and select these surfaces here. Okay, and then we'll generate. Again, we have a nice 3D step over following the contours of these surfaces, and you notice that it doesn't continue all the way down to the parting plane. That's why we have the horizontal finishing that's going to take care of these areas here. So if you look in the top view, you'll see that it covers these areas on the part completely. Okay, so let's go to this view here, and let's show you some other advanced 3-axis methods that we can use on this part. Let's go to 3-axis Advanced, and let's do the between two curves machining. That's right here. And what this does is this lays down a constant 3D step over between two curves of the model. And we will select some additional curves. Let's try those and pick generate. Okay, so we have a constant 3D step over that's the toolpath morphs between this curve and this curve here, following the geometry of the part. So let's do that again. Let's clone that, and this time we'll remove those, and we will use this curve and this curve. We'll generate. So that takes a nice draping surface down across that region. And also let's go ahead and do a curve machining method, and this is a advanced 3-axis method as well. We're going to go to 3-axis Advanced, and we're going to select curve machining. And what this does is it machines along a given curve, and you can machine on the curve and on both sides of the curve. So let's go ahead and do this by curve edges. We're going to go ahead and select this here, and I'll work our way down. And work our way up here. Okay. So there's our curve regions selected, and let's go ahead and go to our tool. We'll select the ball mill. For cut parameters, we can machine on the curve, along the curve, or across the curve. So in this example, we'll go along the curve, and we'll set a cutting bandwidth of 0.1. This is the width of the total cut. So in this 0.1, you can, so we're going to, along this cutting bandwidth, we're going to step over a distance of 0.02. Okay, so let's generate this and see how it looks. Okay, so you got a three-dimensional toolpath that's following the selected curves that we created, and it steps over 10 thousandths or 20 thousandths, and there's a total bandwidth of 0.1 on either side. So you can use this to do touch-ups in certain areas of the part, and all you need is a curve. And you can do this, you don't have to have a closed curve. You can remove those and just have one single curve and generate that. So you can use that for all different kinds of cleanup operations. Anywhere that you have an edge that you can select, you can run a path along that edge to clean it up. Okay, so let's do one more 3-axis advanced method to clean up these bottom edges. I know we had a horizontal finishing here, but we're going to use a pencil trace operation, which creates a toolpath based on the bitangent region of the tool and the part geometry. So if you just come down here and put a profiling operation in there, you will end up cutting more away from your part than you're supposed to. So by using a pencil trace, it will determine where that ball mill can travel in order to be tangent to the part as well as laying on the parting surface. So let's go ahead and see if we can create one of those. We'll pick 3-axis advance. We'll pick the pencil trace operation, and we'll remove that drive region. And what we're going to do here is we want it to calculate the pencil trace areas inside of the entire part. So we're going to select this offset curve that we already have created, and everything inside of that offset curve will be included in the computation. So let's go to the tool, and we'll use the 1/16 ball mill. And then for clearance cut parameters, we're just going to use a cut directional climb, and we're not going to do multiple cuts. We're going to let it determine one cut to clean up that area. That should be sufficient. For the advanced, we don't need any advanced parameters, and for entry exit, we'll go ahead and leave those as linear entries and linear exits. Let's generate that. Okay, so here you see it calculated a toolpath at the base of the part and the parting plane in order to clean up that area of the model. I hope that helped to give you a better understanding of the benefits of the 3-axis advanced toolpath methods that can be used for machining mold cores and mold cavities.